A huge thanks to Brian for sponsoring this video. Bratwurst! It's that time of the year again. The time that my 98% of male watching audience enjoys the most. Papa in tank top. That's my merch. You can find a link to my Teespring shop and also stamage.eu and stamage.com down there in the description if you're interested in 57 Best Prime. Other than that, today, 2014 Hong Kong Maths Olympiad. Yes, we are finally in the Asia part of the world. Asian Maths Olympiad is wild. Find the last 3 digits of. This thing right here is the so-called floor, meaning if you have 3.2, then taking the floor of that is 3, okay, rounding down to the nearest integer. The floor of the cube root of the square root of 5 plus 2 plus the cube root of the square root of 5 minus 2 to the 2014. This is what we need to find the 3 digits of, the last 3 digits of. And it's a very fun problem. I really enjoyed this one. You know, I'm a sucker for roots. Maybe because I really like plants. I have so many plants in my garden. Never mind, this really doesn't matter. And I hope you are going to enjoy the video. Try it out for yourself before watching. Yeah, how would you start with a problem like this? Actually, I simply took a look at the base here at first of the 2014. Let's ignore all the ceiling and the 2014 stuff for now. We want to figure out what this base right here actually is, because there's actually a nicer form than this weird stuff that we got right here at the moment. At first I just went the route of cubing this thing, and it worked out to a certain degree, but it got really messy very quick. This is why I introduced a certain change of variable. So let's at first say that the base is b, okay? Let b be equal to, okay, our base consists of 2 things added together. Let's just call this s and t. So b is equal to s plus t. Now, if we were to cube both sides, then what we're going to get is that b cubed is equal to s plus t cubed. But s plus t cubed, we are just going to derive it really quick. The binomial is the same as s plus t times s plus t squared. And most people should be familiar with what s plus t squared actually is. This is the same as, okay, so we got the factor of s plus t times, then we're going to get s squared plus 2 times st plus t squared. Okay, so far so good. So we got that b cubed is the same as those two multiplied together. Let's multiply everything out and then let's group common terms. We're going to get that b cubed, the b movie cubed is equal to, okay, let's start with the s part. We are going to get s to the 3rd power plus 2 times s squared t plus t squared times s. Then the t part is plus s squared t plus 2 times st squared plus t cubed. And if we were to bring all of those together, we are going to get that our expression cubed, our base cubed, is the same as, okay, we got s to the 3rd power, also we got t to the 3rd power. Let's just scratch everything that we have used already. Then we are going to get 3 times s squared t, because we got this part right here and also s squared t, so plus 3 times s squared t. Plus, and the same here, just with t squared instead of s squared. So plus 3 times st squared. Now the cool thing about this part that we got right here is that we can factor out some stuff. For example, 3 is a common factor. And also, if you take a closer look, we have that s times t is also a common factor. This is going to make matters way easier in a second. Now, what is still left in parentheses here? If we take 3 times st out, on the first term we still have s left, and then likewise on the other term we have t left. Okay, this is what our base cubed is for now. We're going to get that our base cubed is the same as s cubed plus t cubed plus 3 times st times s plus t. And the cool thing about cubing our basically our summons here is that we get rid of the cube root here. So if we were to cube our first part, we are going to basically cancel out the cube root, giving us just what we have right here as the radicand, giving us square root of 5 and then plus 2. Likewise, with t cubed, we are going to get rid of this part right here, the cube root once again, giving us plus square root of 5, but this time minus 2. And the 2's are going to cancel out, giving us just 2 times square root of 5. Now let us deal with s times t. So s times t are just those two roots basically multiplied together. And the cool thing about roots is, if we take a look at, doesn't matter, the nth root of a times the nth root of b, if at least one of these is positive in there as the radicand, both are positive, this makes matters way easier. We don't need to take a look at any complex solutions here. We can actually just multiply the arguments together. It's multiplicative, so this is going to give us the nth root of a times b. Meaning if we were to multiply those two together, we are going to get the cube root, I'm going to put it here, of square root of 5 plus 2 times the square root of 5 minus 2. And you should notice something here, namely that this is just a difference of two squares. This is a plus b times a minus b, meaning this is going to give us the cube root of, so if we got a squared, this is the square root of 5 but squared, which is just 5, and then minus, on the difference of two squares, 2 squared, which is 4. And the magic happens here, because 5 minus 4 is 1, and the cube root of 1 is obviously just 1. Meaning this part right here is actually just 1, giving us overall the process, so we got plus blah blah blah, that b cubed is the same as 2 times the square root of 5. And what we still have left is plus 3 times s plus t. Do you recognize what s plus t is? I left it here. I mean, adding those two terms together isn't easy. Hey, this is where we started at. This is just our base b, obviously. Meaning, we got this cubic equation right here that we need to solve. We need to find the zeros, basically, of b to the third power minus 2 times square root of 5 minus 3b is equal to 0. And that's exactly what we are going to do. You can grab yourself the cubic formula. That's certainly a thing, but no one knows it in their head, and we all get depressed if we use the cubic formula. Thumb up and comment if you got what I just did here, what this little pun was. But we can actually go a bit further and just factorize this very nicely. It's actually rather easy using the difference of cubes. First thing I'm going to do is I'm going to drag the 2 times square root of 5 to the other side by subtracting it, giving us overall that b to the third power minus 2 times square root of 5 is equal to 3 times b. And what I want to do is I want to somehow turn this part into a third power. This is actually rather easy. What we can do is we can smartly add a 0 on the left hand side. Adding a 0 is the same thing as taking something and taking it away right away. What I'm going to do is here, I'm going to subtract 3 times square root of 5, and I'm also going to add it right again, giving us overall that b to the third power minus 2 times square root of 5, and then minus 3 times square root of 5 plus 3 times square root of 5 is still equal to 3 times b. So how is this any useful? I mean, if we take a look at this part right here, this is going to give us negative 5 times the square root of 5. This is where exponent rules come in, and I think the solution is very clever. It took me a while to figure it out. Actually, I took a different route at first by just guessing, but I think this is more elegant, because this way you can actually see that there are also complex solutions that we don't care about in this problem here. Now, if we take a look at the exponents here, we know that 5 is the same as 5 to the first power, so minus 5 to the first power, and square root is actually the same as to the 1/2 power, so 5 to the 1/2. Now, by the exponents rules, if we have the same base but different exponents, what we can do is we can take the same base and then we can just add the exponents together, giving us negative 5 times 1 plus 1/2. And 1 plus 1/2 is the same as 3 over 2. So this is negative 5 to the 3 over 2. Now, we can also make use of another exponentiation rule, namely if we have a to the n times m, this is the same as a to the n to the mth power, meaning we can also say that this is negative 5 to the 1/2 power cubed. And 5 to the 1/2 power is just the square root of 5. Let us rewrite everything, okay? That was maybe a mouthful, but it's going to be worth it in a second. Also, I'm going to bring the 3 times square root of 5 to the other side by subtracting it, giving us b cubed and then minus the square root of 5. But the whole thing cubed is thus equal to 3 times b minus 3 times the square root of 5. Now, here on this right-hand side, you can see that we have 3 as a common factor. Okay, let us factor it out. And now we got the difference of cubes here. I don't believe that many people have this formula in their head right away. So let's derive it from scratch real quick using just basically the geometric series. It's very easy. So geometric series is something that we already know here on this channel. If you're not familiar with it, check it out here on my channel. Have a lot of videos on it. So if we have 1 plus x plus blah 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 up until x to the nth power, we can actually rewrite this by basically just summing it up with nearly the same summation. We are going to get 1 minus x to the n plus 1 power divided by 1 minus x. This is just common knowledge. This right here is the geometric progression. Now what we can do is we can multiply both sides by 1 minus x under the condition that it's not equal to 0, meaning x not equal to 1 in our case. Then we are going to get that 1 minus x times 1 plus blah 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 up until x to the nth power is the same as 1 minus x to the n plus 1th power. This is going to help us in our case up here. I'm going to rewrite what we have up here for now. Let's say we have a plus b and no, a minus b, we want the difference of cubes, and all of this to the 3rd power basically. Now what we can do is we can factor out an a to the 3rd power here on both terms. If we factor this out, we get a to the 3rd power times, and then we are going to get 1 minus, because we factor out the a to the 3rd power. We don't have an a to the 3rd power here, so we have to divide by it. So b to the 3rd power divided by a to the 3rd power. Exponentiation rule says that we can just basically factor out the to the 3rd power. Okay, so we are going to get this right here. And if we take a look at 1 minus blah 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 to the 3rd power, you're going to notice this is just what we basically have up here, with n being equal to 2 in our case. And if we drag this to the other side, we are just going to get that a to the 3rd power minus b to the 3rd power is equal to a to the 3rd power times, and by the geometric progression we are going to get 1 minus x in our case is b divided by a times, and we have n being equal to 2 here, so we are going to get 1 plus our x is b divided by a plus b squared divided by a squared. It's that easy, and now we can distribute our a to the 3rd power into these factors separately. We're going to distribute 1a into here, giving us a minus b times, and the other a squared we're going to distribute it into here. We're going to get a squared plus. On the a squared term here, our a is going to cancel out, giving us just ab as the middle part, plus, and the a squared is going to cancel out with the a squared completely, giving us just b squared. And this right here is our difference of cubes formula, namely that a to the 3rd power minus b to the 3rd power is equal to this stuff. And if you've never seen a derivation of this using the geometric progression, here you go. It's very elegant, at least in my opinion. And this looks like a very crooked dick. Never mind. Now, we know what our a and our b are respectively. In our case, our a is b up here and our b is square root of 5, meaning by using the difference of cubes, we are going to get that b minus the square root of 5 times, and now we are going to get b squared plus b times the square root of 5, so square root of 5 times b, it's commutative, and last but not least plus b squared is going to be the square root of 5 squared, which is nothing other than 5. And all of this is equal to 3 times b minus the square root of 5. Now you cannot just divide both sides by b minus the square root of 5, because we don't know if it's equal to 0. We're going to take the smart route and we're going to subtract 3 times b minus the square root of 5 on both sides. If we were to subtract it, we're going to get something of that sort, something being equal to 0. And you're going to notice that b minus the square root of 5 is a common factor, so let us factor it out. We're going to get b minus the square root of 5. And then what we're going to get is just this part minus 3 by factoring out the b minus the square root of 5. This is what we're going to get. So we're going to get b squared plus square root of 5 times b, and then 5 minus 3 is going to give us just 2. And all of this is equal to 0. And here we go. Now we are at the stage where we can actually do cases. A multiplication of things is only equal to 0 if one of the parts is equal to 0. So either we can have that b minus square root of 5 is equal to 0, implying overall that b must be equal to square root of 5. This is one of the solutions, actually what we got right here, in parentheses, as our base is equal to square root of 5, but we are not done yet. It's a third-degree polynomial, meaning we also need to check if or b squared plus the square root of 5 times b plus 2 is equal to 0. I mean, this is very easy business by using the quadratic formula. We are going to get two solutions for b. We get square root of 5 with a negative sign in front divided by 2 plus or minus the square root of, okay, square root of 5 divided by 2, all of the squared is going to give us 5 over 4, and then minus 2. Now, if we were to expand this, we are going to get 8 divided by 4, meaning right here in parentheses we are going to get negative 3 over 4. This poses a problem because that means that both other solutions that we get for b are actually complex. This is not going to be the case here. Why is it not the case? Those two solutions, we don't care about them because if we take a look at this part here, square root of 5 plus 2, this is going to be positive, meaning we're going to get a positive third basically, not a complex number, at least one of the branches, okay? And if we take a look at this part here, square root of 5 minus 2 is still positive. Actually, it really doesn't matter anyways. Even if the cube root is negative in the argument, we can just drag the negative sign to the outside, at least for the first branch, you could say. But other than that, we don't care about the complex solutions here. All we need to know is that what we have here as the base is equal to square root of 5, meaning our original problem is going to reduce to the floor of, and then we are going to get the square root of 5 to the 14th power. And yeah, now we need to find the last 3 digits of that. Cool thing about powers is once again that we can make use of this exponentiation rule that a to the n to the mth power is the same as a to the n times m. So we are going to get the floor of, and don't forget square root means to the 1/2 power, 5 to the 2014 over 2. Yeah, this reduced quite nicely, and 2014 over 2 is the same as 1007. So floor of 5 to the 1007th power. This is just an integer raised to some power. It's going to be an integer overall, meaning we don't even need this integer part right here. It was just there to confuse the MO participant. Now 5 to the 1007th power, this is 5 to some odd power. Let us figure this out real quick. So if we get 5 to the first power, this is 5. 5 squared is 25. And we only care about the last 3 digits. Times 5. This is going to be to the third power, so this is 1, 2. To the third power is 125. Then we are going to get, maybe you can spot a pattern here. Last digit is always going to be a 5. Then this times 5 is 500 plus 125 is going to give us 625. Okay, the last 2 digits are always 25. We only care about the last 3 digits, so we don't care about the bigger number at the front, all the bigger numbers. 625 times 5 is going to give us 3,125, if I'm not mistaken, 3,125. This is once again on an odd iteration, but we don't care about this number up front. In the digit decomposition, if we exponentiate it, it really doesn't matter. So 125, and if we were to if we were to take this to the 5th power, was this a sensic? No, I don't think so. Never mind. There was a short I once did. We're going to get something with 625 once again, 15,625, and so on. And this on the 6th iteration, 625, and so on. If we were to take this to the 5th power once again, this is on the 7th iteration, 125, and so on. Really doesn't matter. For the higher terms, on each and every odd iteration, odd power, we are going to get 125 as the last 3 digits. And this concludes today's problem. And I think this was a very elegant solution, and it was a lot of fun to solve. Did you come up with a different way? Let me know down there in the comments below. I would be very interested, especially how you were able to solve this part. I think this factorization was absolutely brilliant. Talking about brilliant, there was a smooth transition. Have I ever told you about today's sponsor, Brilliant, who are kind enough to sponsor yet another video here on this channel? Hear me out, it's an amazing platform. Now, if you're not familiar with Brilliant yet, do not worry, here's a short and spicy introduction. Brilliant is your platform for some of the most amazing interactive learning content out there on the internet. It's actually one of the only platforms I know about which offers such a high quality educational system. It's seriously brilliant. The name suggests it, and they actually deliver big time. With the nearly 70 interactive courses in all topics STEM, be it the mathematics that we did today, contest mathematics at that, physics, computer sciences, chemistry, no matter what it is you're striving for to learn in the STEM field, Brilliant got something up their sleeve for you. And their course concept is actually very easy to grasp, but highly effective, seriously effective. Even I learn a lot of new things when browsing through Brilliant on a weekly basis. The courses start off very easy, getting progressively harder over time, giving you a better understanding in the process of the topic at hand. But more importantly, all of their courses are backed with a lot of interactive content. Things that you can grab with your own two hands by taking your mouse, and then you can take a look at pictures, grab on the corners of a triangle, take statistical data and play around with it, interpret it in a graph, varying the parameters. The things you can do are nearly endless. It's crazy. They have so much content available on their website already. And the best way to experience Brilliant is by experiencing it for yourself, by trying it out, by checking out the link at the top of the description, brilliant.org/FembleMaths. With it, you are going to get free access to a big portion of Brilliant already, but more importantly, the first 200 people that actually make use of the link get 20% of an annual premium subscription, which is a freaking great deal considering so much content they have available on their website already, and they are adding new stuff on a regular basis. So definitely make sure to check it out and support the channel this way. So yeah, if this sparked your curiosity, make sure to check it out. It's a seriously good website. I just love to use it. I'm seriously using it, even in my classes. My students speak German. I'm using an English website for education. This really speaks for itself if you ask me. So yeah, those are the last words from myself for today. And don't forget to also check out Flammy's Wood, my woodworking channel, and STEMage.eu and all this crazy stuff. And up until next video, I wish you guys a very square rooty day. Oh, that is good, that is good. Can I make my neck? Oh, did you hear that? I'm getting old. My shoulder have a flambe day. Ciao.